Hello everyone, welcome to Statistical Foundation of Big Data Analysis. We continue our discussion of hypothesis testing. Today I wanted to review little bit of what we discussed last time, and not that I generally do that in every class, but today I wanted to repeat some of the things what I did last class, just to emphasize. So as statistical inference is basically making decision about sample based on population based on sample, and we saw that we do two kinds of statistical inference, estimation and hypothesis testing. In case of estimation, we basically have sample, utilize the sample to get some answer about the population parameter. In case of, so basically the type of question we are asking, we really do not have any a priori information about those questions except some very abstract theoretical answers. For example, if you are looking for average height of a person living in Antarctica, this was the first example we were discussing last time. Saying we no idea is already a very subjective thing. For example, average height will be a non-negative real number. We are not talking about that. That's something very that just follows from the nature of reality, that a height of a person is non-negative. But is that information interesting? So that information is just doesn't give us any insight. The hypothesis testing is something where we have some existing insight, not just existing insight, it may be we have some existing goal of this analysis, existing goal for this analysis. So for example, if the question 2 is the average height of a person living in India is above 7 feet. The point is there are many subtle layers here when you are comparing these two questions. Here it's a straightforward question where of course we know that the height will be a non-negative number, non-negative real number, but that's it. Here the moment you look at this question 2, and you see these two words, India and 7 feet, above 7 feet, something clicks in your mind. You know that average height of a person in India probably not above 7 feet, it has to be probably less than 6 feet. But you have an intuitive understanding of what's the height of an Indian is. Now this conventional wisdom is something you want to utilize. I'll just go straight fast and go to this rather morbid example we did. The conventional wisdom in the height example is of one type. Conventional wisdom here is of a different kind. Here, this is also an example we carefully discussed last time. Here a doctor is testing a patient's tumor. A patient with tumor has come to a doctor. Doctor has to take a call whether he say that the patient doesn't have cancer or the patient has cancer. Here also there is some layer in this analysis. Statistics is a very real life science. As some people say, statistics is the science of deductive reasoning, statistics is the science of inductive reasoning. You kind of collect inductively, you collect data from a population, and from that, based on the data you have collected, you make some conclusion. But then once you have made some conclusion about the population, that conclusion can further be validated by future data. So more data you collect, or once we have analyzed and come up with some conclusion, in future there can be another analysis, and that will improve, that will potentially so once you have collected data from a population and come up with a decision, you have that decision becomes part of the record. Now in future, when you're interested in, let's say, some other question that may be related, that may be unrelated, before analysis probably you don't even know whether they are related or not, maybe you have some tacit understanding, but when you are interested in in future for some other analysis, some other test or other study on the same population, you have two choices. You will collect sample, that's fine. Whether to utilize the knowledge that you have already collected in this first analysis or not utilize it, the knowledge can be irrelevant. But if the knowledge is relevant, you really need to utilize that knowledge and potentially improve on that. That's what you were doing in hypothesis testing. There is some evidence, already existing evidence, existing knowledge, existing information. When you are collecting some new data, you really don't have just that data, you also have the previous evidence. Your analysis has to take into account of both of them. Of course, if it's not relevant or something is not known, you don't have a data of some information about previous tests, then you just have the data. So this is what happens in statistics quite a lot. You have some analysis, you have a question, you analyze, come up with a result, keep the result. In future, you are interested in some other question, maybe related, maybe not. You face this question whether to utilize this previous result or not, and maybe you utilize it and improve on the existing result. So that's why inductively you keep gathering information. So this is what happens in statistics. So this was another example, like not very similar to this question is not very similar to this question 2 in average height of an Indian person is more than 7 feet or not. But here also there is something, there is some purpose, so this question, for example, a person goes to a doctor, doctor sees the patient, there is something more beyond this simple incident. Doctor potentially want to be very safe, doctor potentially want to not miss the detection of a disease which is potentially malignant, because that has consequence. So if you think as a status quo result, just like status quo information in that height question was, or existing information, or let's say a starting point in that example was Indians probably do not have average height of Indians probably is not more than 7 feet. Here the starting point is, it's better for the doctor to avoid making one error over another error. The two types of errors doctor can do are not symmetric. They do not have consequence of same magnitude. One of them has far worse consequences than the other error side. So this by default, the default choice in an analysis, if there is some default choice available in that analysis and there is an alternate choice, that's what is the scenario of hypothesis testing. So this is what we were discussing in the key components. So for a key component, so the framework of a hypothesis testing in a statistical hypothesis testing is, you want to find a rule which so you want to find a rule that you have a sample, that rule will give you something from that sample. Based on that, so you have a sample, you will calculate a sample statistics as in the case of estimation, and then there will be some rule. Based on that rule, if the sample statistic takes certain value, you will compare two statements based on that certain value. There will be one of them will be the assertion, status quo thing to do, conventional wisdom, etc., and the other one will be an alternate. So based on the value of the sample statistic, sample collected from the population, you will decide between assertion and the alternate. Now between these two, which one is assertion, conventional wisdom, starting point, and which one is alternate will depend on the scenario. Here, even if you have collected a sample and the average height comes above 7 feet, it is very suspicious. You want further test, further analysis, further sample collected to confirm that, simply because you are saying your existing knowledge is saying something is not right. Similarly, here it is not enough to just see one symptom or few symptoms of the tumor and say, okay, the person does not have cancer, because being wrong, because you can only test finitely many or few symptoms right away when you are seeing the patient. it's better to be safe here. So here the starting point here becomes something just like here, the starting point becomes the conclusion whose rejection should not be done in haste, namely conclusion that average height of an Indian is less than 7 feet should not be dumped in haste, because that's the conventional wisdom. Similarly, here the conclusion that potentially the patient has cancer should not be dumped in haste, because if it is dumped in haste, the consequence can be very serious. So, between two statements, now we are in this situation, we want to compare two statements about a population using some sample and some statistic based on that sample. Assertion alternate. Reality is assertion is true. Reality, there are two possibility in reality can be assertion is true, assertion is false, and that there are two potential decisions. You reject assertion or reject the alternate. The first type of error, when assertion is true, you are rejecting the assertion. This is one type of error, and another type of error is that assertion is false, but yet you are rejecting the alternate. This is another type of error. The more serious error, we name it as type 1 error, and amongst these two statements whose rejection, wrong rejection, leads to type 1 error or the more serious error, we start with that as our assertion and design the test. So, this is something you have to understand. There is between two statements, which one is assertion, which one is alternate, that is which one is we call the assertion as null hypothesis and alternate is the alternate hypothesis. Which one is null hypothesis, which one is alternate hypothesis purely depends on the test and what you are trying to achieve from the test. In case of this patient with cancer, obviously the doctor's target is to cure the patient. Similarly, in case of height greater than 7 feet or not, the tacit assumption, the moment you face such a question, obviously you are expecting the answer to be wrong, but still your testing means you have a suspicion that that may not be the correct thing, but most likely it is wrong, that average height is not greater than 7 feet, but maybe some disease of becoming giant has occurred. You want to test that, but that's very unlikely scenario, or maybe, well, not disease, I mean that will not be hard to detect, but something may have happened where the average is coming out to be that. So, there you really want to protect the conventional wisdom that this is less than 7 feet. So, this is what decides what's null hypothesis, which one whose false rejection is more serious. So, the job of the hypothesis testing is to decide whether there are overwhelming evidence to reject the conventional wisdom starting point or null hypothesis. So, as we discussed that, like ultimately what you will have to do, you will have to come up with a rule based on which the rejection will happen. So, ultimately you have collected the sample, you have to come up with a sample statistic, that is a rule that will give you a number. So, we will first of all have to come up with a number, a method that will give you a number based on the sample, and then you have to come up with a rule that if that number belongs to this region, you reject the alternate, and if it belongs to this region, you reject the null. So, critical region we define is that if the value of the number, that test statistic is in this, then the observations are overwhelmingly more likely to come from H1 than H0. So, you reject H1 if the evidence is overwhelming, you reject H0 if the evidences are overwhelmingly more likely to come from H0 than H1. So, here you reject the null hypothesis if there is, you are absolutely sure the patient does not have a cancer. You do whatever tests you can, you collect data as much as you want, you are absolutely sure it is not cancer, then only you say, okay, fine, go home. So, this is what the goal is. So, type 2 error and type 1 error, when H0 is true, you reject it, that is you wrongly reject null hypothesis, and type 2 error, when H1 is true, you do not reject this. That is, when null hypothesis is wrong, even then you accept the null hypothesis. So, as null hypothesis is status quo, this is type 1 error is more serious. So, this is an example we discussed. So, if you are testing between, so you have a coin tossing situation, you are testing between head probability half and head probability 0.6. Basically, this is the situation where the coin is a fair coin, that both head and tails are equally likely. The thing is, quality of your decision is something can be measured using type 1 error and type 2 error. If either of the probabilities, that is type 1 error, probability of type 1 error and probability of type 2 error, either of them is very high, then your test is not very good. But if they are moderate, then maybe your test is decent. So, say this is your rule that reject H0 in favor of H1 if out of 10 tosses 7 heads are observed. This is a binomial situation, binomial 10p. So, you can test that under, when null hypothesis is true, the probability of x being greater than or equal to 7 is 0.172, that is the error of probability of type 1 error is 0.172, and similarly probability of type 2 error, that is probability of getting less than 7 when p is actually 0.6 is 0.618. Here the type 1 probability of type 2 error is pretty huge. Type 1 error is actually something we are more serious about. This is comparatively less, but type 2 error is pretty big. So, this is probably not a very good test. So, if you change the rule, if this is the rule x greater than or equal to 7, here we know that it is 1.7, well, this is 1.7172 and this is 761. So, this is basically so the type 1 error here is this and the type 2 error is this. For x greater than or equal to 6, type 1 error increases, type 2 error decreases. So, basically when x greater than 6, you are rejecting more. So, you are rejecting null hypothesis for bigger area. So, of course, if you are rejecting null hypothesis more, the potential of type 1 error will increase, but then you are rejecting null hypothesis more, so potential of type 2 error will also decrease. If it is 8, of course, type 1 error will be bigger, smaller than 7, the original one you discussed, because you are now even more protecting the type 1 error. But look, if you are protecting type 1 error more, type 2 error has also increased. Further protecting type 1 error going down, type 2 error is increasing, and this is very low type 1 error, but very high type 2 error. Now, intuition says collecting larger sample gives better prediction, because sample keeps growing, then it eventually becomes the whole population. So, let us see what happens if you are, instead of doing 10 tosses, if you do 100 toss. For 100 toss, for 10 you are rejecting, your rejecting null hypothesis rule was greater than or equal to 7, that was type 1 error, this was type 2 error. Look at this, proportionally 70 is out of 100 is same as 7 out of 10. Probability of type 1 error is so little, but type 2 error is unfortunately is bigger. You can calculate these using binomial probabilities. For now, instead of concentrating on the calculation of binomial coefficient, see the pattern. If you want to reduce type 2 error, of course, you have to increase the rejection region, make it 60. Type 1 error increases, type 2 error comes down. 55, type 1 error increases more, type 2 error also increases to 113. Now, if you compare this with this, greater than or equal to 7 gave you type 1 error 0.171 and type 2 error 0.61. Here already 55 is giving you more or less similar type 1 error and drastically low type 2 error. 56 even better, type 1 error is actually better than this situation, less, and type 2 error is pretty much less. 57, type 1 error even less, type 2 error somewhat more. Already the situation gets better. You can choose a finer rejection rule. Here we saw that 5 is not, definitely 5 or 6 is not going. 6 already has type 2 error 0.37, so choosing 5 will be much worse. But here on the other hand, 55, 56 is giving you fairly good rule. Take sample size 1000. Type 1 error for 530, type 1 error is 0.03, which is better than any of these, and type 2 error is so less. 527 is more or less similar. So if you make the sample size 10,000 or 1 lakh, situation will get even better. So if you want to reduce, come up with a rejection rule which will give you much better type 1 error and type 2 error, that is probability of type 1 error and type 2 error will be very low, then the rule has to be based on a larger sample. So the lesson here is that the better idea you want, even in hypothesis testing like estimation, the better idea you want about how these two statements compare can be obtained, better idea you will get from bigger sample. So bigger your sample size is, better the idea will be. So if you want to reduce both type 1 error and type 2 error, keep collecting data. So this kind of testing hypothesis, this need not be of course for the discrete setup only. So here is an example where we do hypothesis testing for continuous population. The usual normal population, X is a normal population with mean mu and variance sigma square, where mean is unknown and variance is known. I mean, we do hypothesis testing for unknown variance also. I'll get there. I mean, this is basically, if you recall this this from confidence interval talks, like this Z distribution versus T distribution utilizing. So in case of sigma unknown, utilizing T distribution or chi-square distribution, these kind of things will come into the picture. But let's discuss as a starter for continuous setup the known variance case, hypothesis testing for population mean for known variance case. Now let's draw an IID sample x1, x2, xn from a normal mu sigma square population where mean mu is known and variance sigma square is unknown. So mean mu is known and variance sigma square, sorry, please cut আবার শুরু করব. Retaking last few slides of lecture 14. Now hypothesis testing, just so far we saw this coin tossing example only, but the philosophy and the questions that we discussed should already indicate that nothing specific about discrete setup. One can do it for continuous setup also, and as a starter we will do the example, the most basic example of hypothesis testing of normal population mean for populations with known variance. I mean, one can do this for unknown variance also. In fact, we will do it in in next class probably. For unknown variance, like in case of confidence interval, one has to utilize these other sampling distributions like T, chi-square, etc. We will see that when we discuss that. But for now, we are interested in testing two hypotheses. One is the population mean is equal to C1, a fixed value C1, and versus population mean equal to C2. So mean equal to C1 is our null hypothesis, the status quo, and mean equal to C2 is the alternate. So here we are working on with the case C2 greater than C1, and accordingly the rejection region will be decided. So imagine a baby food company is trying to launch a new product. So they will have to compete, let's say, the existing market leader in baby food, let's say, I don't know, Lactogen or Nan or whatever. And for the market leader, let's say the average weight gain in 1 month is C1 for the existing market leader. Now the point is, the new product, before they launch their product in industry scale, they would like to do some statistical analysis and survey to assess whether it's business, it's a it's a viable business to launch their product or not. Of course, they would like their product to be better. In a sense, it should, for newborn babies, gaining weight was generally is a very big concern, because doctors think that if the properly weight gain is not happening, brain development will not happen. So generally speaking, more weight gain happens is better. Of course, there are other aspects, but that's let's focus on the weight gain part first for this example. The new product, the company will hope their product will deliver average weight gain better than C1, but not just better. It has to be significantly better. The reason for that, not only it's not just enough to be better, because when you are fighting against a market leader, you also will have to fight with its reputation, its trust amongst the doctors, users, etc. So when you are launching this product, it has to be significantly better to be a viable business. So basically, so this is roughly the normal graph. If this is C1, so this is the graph of C1. If your average, sample average, the normalized sample average, so you draw a random sample from this population x1, x2, xn, you do the same thing, you know that this is a normal population, so the mean, sample mean is also normal. We just saw sample mean is normal with same population mean, and variance gets divided by n. So under C1, if C1 is the population mean, under this assumption, this follows C1 sigma square n. So suppose this is the graph for n C1 sigma square n. Now the thing is, the alternate is mu equal to C2. If your guess is that alternate is significantly more likely than the null hypothesis, let us say C2 is here, what consists of evidence in favor of C2 significantly more than C1? The value, if the observed value for x bar is somewhere in the left, is that an evidence in favor of C2? The answer is no, because if the mean actually is C2, I mean more likely the mean is C2 than C1, the probability of being left of C1 is even less. Chances of being left of C1 is even less, because simply we are working under the assumption C2 is bigger than C1. So the only thing to get overwhelming evidence, not just evidence, first of all to get evidence in favor of C2 rather than C1, it has to be right of C1, of course, because anything left of C1, because it's even farther left of C2, and given the curve of normal, given the bell nature of normal curve, anything left of C2 will be more evidence in favor of, anything left of C1 will be more evidence in favor of C1 than C2. Anything left of C2, of course, will be more evidence in favor of C1, but is it significantly more evidence? That's what we want to emphasize. So it has to be not only just left of C2, it has to be far enough such that this is significantly more likely to come from mu equal to C2. This is what we are targeting. We want significantly more likely to come from C2. So that's what we are aiming at. So to get type 1 error, probability of type 1 error, you reject C1, you reject C1, that is, you reject H0 when actually H0 is correct. Of course, rejection region, as we saw that because C2 is, because now you work with standard normal curve, your test statistic Z is x bar minus C1 divided by sigma square root n. You work with standard normal curve, and you saw that because C2 is left of C1, the rejection region has to be on further right. Now, suppose this is your rejection region, you are looking for what will give you type 1 error to be alpha. Now, because the rejection region is in this site, to get type 1 error, that is you reject H naught when mu equal to C1, you want this probability to be alpha. So, this probability has to be 1 minus alpha. This is the point Z alpha, which can be calculated from normal distribution table. So, basically you want probability of x bar minus C1 divided by sigma square root n. This has to be so probability that this be greater than equal to this point Z alpha. This is equal to alpha because this is n01. This can be found from table, known table, normal table, and then you just do simple algebra to find the value for the rejection region using just x bar. So, this is how you calculate the type 1 error. So, the point is, what is the probability of rejecting it, of not rejecting it under C2. So, it boils down to what is the probability of getting x bar less than this value decided in type 1 error step when mu is C2. Well, if x bar is less than this, then x bar minus C2 over sigma over square root n will be less than equal to this. So, that will just be probability of this. So, generally speaking, beta is the notation for type 1 error, type 2 error, for beta notation for type 2 error, and alpha notation for type 1 error. So, this is generally standard in the literature. So, this is how type 1 error and type 2 error are calculated in this case, and note that this is basically this one basically can be. So, this is standard normal 0 1 if mu is actually C2. So, this can be calculated using normal table. So, this is how basically hypothesis testing for continuous setup done. I stop this class here. Thank you. We will pick up from this next time and do some numerical example.